This museum exhibit, entitled Tools of the Future, has the purpose of solving the grand challenge of engineering the tools of scientific discovery. To do this, we have designed our exhibit to inspire the next generation of engineers to think bigger and expand their horizons about what a tool is. By doing this, we are enabling current and future generations to develop the future tools used in scientific discovery. Here's the objective.
We want to show the youth just what a tool can be. We want to break down the stereotype that a tool is just a hammer and show to everyone how a tool can also be something incredible, like a rocket or crane. When people understand a tool can be anything, then the chances of discovery skyrocket, and we can advance into the future together.
Here's what we need to design. An exhibit that makes science and engineering fun and accessible to kids, something that will stand out to a kid in our age range of 5 to 18, will engage 10 kids at once, will engage kids for 3 to 5 minutes, and is low maintenance. Our potential customers are any museum looking for an exhibit to inspire future generations of engineers to think larger and inspire them to make more advanced tools for scientific discovery.
Our final design easily meets all of our initial design criteria and is easy enough to make given our constraints. A great success, we were able to stay well within our $150 budget. For power, our exhibit will run off of a battery pack, or could potentially be hardwired to run off of a standard 120-volt outlet. It will accommodate at least 10 kids at a time. Some can play with the crane, others can read our posters, or watch other kids try to stack the rocket. After all, what kid doesn't like watching construction equipment work? The kids at our exhibit will easily be entertained for 3 to 5 minutes and be inspired to create new tools. Our exhibit is also made with durability in mind. No part of our design will have heavy wear even during constant use, except for the batteries. The batteries would have to be recharged or replaced as part as regular maintenance, unless we wall power the crane. Our exhibit is made from a mix of 3D printed components and foam board. All moving 3D printed components were printed at a tolerance of 5/1000ths of an inch. This means that our 3D printed rocket fits together with very small gaps at the seams, and all of our gears in the crane fit very snug. The foam board was used for all of the larger parts in the crane that were too big for a 3D printer. We are controlling our crane with an Arduino and 3 electric motors, all connected through 2 L298N motor controllers hooked up to the Arduino. The motors are powered by 8 AA batteries in series. All of our electronics are mounted to or inside of the crane for simplicity. Our rocket is designed to stack like an upside-down cone to help the kids put the rocket together. All this combined should make for a very fun and immersive experience for the kids, while maintaining a reliable and resilient design.
Our design is very unique because we are explaining the tools that make rockets. Imagine wrenches and screws that make even bigger tools like cars and robots, even rockets. We found the middle spot being the crane that is essential to putting the rocket together to get the final payload in the air. We did it by having an Xbox controller to control all the moving parts of the crane. And we use simple materials like styrofoam and the 3D printed parts to add to the crane design. Our theme is focusing on the youth, getting them interested in science, technology, engineering, arts, and math. Instead of boring them with calculus and art history, we want them to be engaged and be able to interact with our exhibit, and hopefully inspire them to do something better.
Our team wanted to incorporate a tool that most people don't think about when they hear the word tool. We really liked the idea of doing something related to satellites or spaceships because they are underappreciated tools. Then, as we expanded upon that idea, we thought about adding a crane to it to put it together and take it apart. That way, we have an exhibit that exposes kids to 2 different types of tools, both of which are tools that are commonly overlooked and will engage the kids at the same time.
We had to go through a lot of testing and verification regarding our electronics and code. First off, our given kit of parts didn't include all the electronics we needed to control the motors with, so we had to buy some motor controllers, which cost around like $7. After that, we had to come up with a method to supply power to make everything work. We didn't have access to a DC power supply, so this made things more difficult to try and figure out if it was a software issue or an electrical issue. So we had to run a lot of tests with our Arduinos and motors to pinpoint if it was a power issue, which ultimately it was. But this was an easy fix. We just bought more batteries and we wired them in series, and everything started running. But our last issue was our code that interrupted the Xbox controller's outputs and supplied them to the Arduino. Our inputs on the Xbox controller were very jittery to start. We redefined the code by just figuring out what felt right by just trial and error, and I got one of my friends from that is a programmer at this lab to just look at the code, and he helped us out a lot. And now everything just runs smoothly and works, which is perfect.
Over time, our design has gone through many iterations and changes, but there have been two big changes we've made during the design process. The first is making the crane out of partially foam in order to save on both time and money. This was because we were limited in both of these aspects for this project. The second is the rocket and how we simplified it over time. Our original design would have included magnets, which would have been much more difficult to manufacture, and because of this difficulty, we decided to simplify the design and made it so that the parts could just slide on and off of one of each other. This way, we would have much more better manipulation over the rockets and the parts of it.
While our prototype is fully functioning, there are some design changes that if we were to start over, we would most likely change. The first one is instead of using a rack and pinion system for moving the crane forward and backwards along its boom, I would use a belt system where a piece slides along the track and a motor moves the belt forward and backwards instead of having the weight of the whole trolley motor assembly moving forward and backwards along the crane. In addition, all wiring would be secured in place if we were to go with this solution, and it would reduce faulty connections. Another design change would be not having the Arduino on the back, since if the crane happens to fall, which it has, it typically falls Arduino first because that is the heaviest part of the crane, and the way physics works, it's just going to be where it hits most likely. The last change I would make is I would use a higher gear ratio on the pivot motor, as it takes a lot of torque to rotate the whole crane, and fine controls when rotating the crane is difficult due to the high amount of power required to overcome friction and other forces. After seeing our exhibit, you may be wondering how much it all costs. I am happy to report that after adding up all of our costs, our total comes out to $90.53, which is well under our budget of $150.
Our mission is to teach kids about how amazing tools for scientific discovery can be, in order to inspire the next generation of great engineers. Our prototype can do just that, and with just a few tweaks and changes, it is deserving of a spot in a true museum. If kids know what is possible, then they know what they can strive for.